Welcome back to Honors Calculus. In this video, we'll be starting off our lesson on inequalities with a discussion of fields. As I mentioned in the last lesson, our goal here is to try to establish a more theoretical foundation for the real numbers, something a little bit better than the hand-waving idea of there's a bunch of numbers that you can't write as fractions that you probably came across in your previous algebra coursework. So let me get my head out of the way and let's dive right in. I am definitely ahead of myself here. In lesson 5, we will finally get far enough that I can give you officially the definition of the real numbers as the complete ordered field. For right now, I expect that that definition is completely meaningless to you, but I wanted to start off with it, first of all, to give you this blackboard bold or double stroke R, the symbol of the real numbers. We've finally gotten through all of the sets that we're going to be working with. Today, in this video, we're going to be looking at the idea of a field. Field is the generalization of the properties of numbers that you are already familiar with: commutative, associative, distributive, all of that fun stuff. In the next video, we will take a look at what it means for a field to be ordered, and then a couple of weeks from now, we will come back and just with an ordered field, we can do a lot of work. Once we make that ordered field complete, it will give us a few more tools at our disposal. And at that point, we will officially have the definition of the real numbers. Right. So as the title of this video suggests, we're going to be looking at fields. So we can call this field whatever we'd like. F is a very common variable for an abstract field, but as I just said, we're looking at fields specifically to look at the definition of the real numbers. So let's go ahead and call this field double stroke R. A field is a set equipped with two operations, plus and times, such that, and all told, we have 10 properties. Right? The field must be closed under both the addition and multiplication operation. And those operations can be abstracted. We're going to stick with the operations that you are familiar with. But I do like to mention that there is a branch of mathematics called abstract algebra that asks questions about what if these things took on different meanings? How would that change the rules? Right. We're not going to be looking too much at that. We're going to stick with things as they are, or as you're accustomed to. We're closed under both addition and multiplication. And then the properties that you are familiar with. The commutative property. For any two real numbers a and b, a plus b is the same thing as b plus a. Addition is associative. If you have a plus b plus c, you can group the b plus c first, and it doesn't do any problems to the addition. We have a unique identity. The identity of addition is always written as 0. In other fields, that 0 might mean something drastically different from what you're accustomed to, but we always write it as 0. You add 0 to anything, you get back that thing. Right? Each element in the field has an inverse, which we write as the opposite of A, so that if you add A plus the opposite of A, you get 0. And then we go through a lot of the same thing with multiplication. Right? Multiplication is commutative and associative. There is an identity 1 in R such that 1 times A is A. Every element has an inverse, which we're going to write as A raised to the negative 1 power. And then finally, we have the distributive property. Right? All things that you are familiar with, we take this as part of the definition of the real numbers. The real numbers are a set that satisfies this property along with the other two properties. And it's a little bit beyond the scope of our course, but if you go on to take a course in real analysis, one of the big things that you will prove in that course is that there is exactly one set that satisfies all three of these properties. If we were sticking to just a field as our definition, it certainly wouldn't be enough. In fact, the rational numbers are enough to satisfy this idea of a field. The rational numbers are also a field, so we haven't gained anything on the rational numbers just yet. We'll get there a little bit later. But for today, using this idea, using these 10 properties of a field, I want to expand out and get a few other properties. For example, you are familiar with the idea that if you take anything and multiply it times 0, the additive identity, you will get back 0. That's not something that is guaranteed in the definition of a field. That's something that we have to establish. And we can do that by using the properties that we already have. And this is a proof by cute trick. A lot of these proofs are honestly proof by cute trick. But we know that if I take a times 0, well, it's not obvious why I would want to do this, but I could rewrite that as a times 0 plus 0, right? Because 0 plus 0 is 0. So I've taken something that's fairly straightforward and I've made it more complicated. Right? 0 plus 0 is 0. 0 plus anything is that thing. Then I can distribute. A times 0 plus 0 is a times 0 plus a times 0. And then from here, I can subtract. I don't know yet what a times 0 is, but I know that it has to have an additive inverse. So if I take my a times 0 and I add whatever the opposite of a times 0 is, well, something plus its opposite is 0. So a times 0 plus the opposite of a times 0 is 0. And once again over here, a times 0 plus whatever the opposite of a times 0 is still 0. And if you add 0 to something, it doesn't change that thing. Right? By using the property of the identity 0, anything plus 0 is that thing, we get that 0 is the same thing as a times 0, which is exactly what this theorem told us we were going to prove. Playing around a little bit more with 0, one of the most powerful properties that you come across in algebra coursework, the theory of equations, the middle school and high school algebra, college algebra that you have studied up until this point, one of the most popular or one of the most powerful tools in those courses is the zero product rule. let's let R be a field, and let's let A and B be elements of that field such that A times B is 0. You remember from previous coursework that the zero product rule tells us that either A is 0 or B is 0 or possibly both. That's something that you're very familiar with from your previous coursework in algebra. But it's not a property of fields. It's not something that we are assuming is true. It's something that we want to prove must follow from the definitions that we are using. All right. I'm going to start with a WLOG statement. WLOG is an abbreviation we use in mathematics for the phrase without loss of generality. And the purpose of a WLOG statement is to simplify redundancy in a proof. In this case, I have two things I'm multiplying together, and I'm claiming that when the product of these two things is 0, one of the things itself must be 0. If b is equal to 0, then this is about the easiest proof that has ever come up, because we're already done. So that's not the interesting case. Not to say that b can't be 0, but we could name a and b in whichever order we want to. It doesn't matter whether we study what happens when b is not 0 and show that a is 0, or if we show that a is not 0 and that means that b must be 0. So we can simplify that redundancy by just saying, let's say that b is the not 0 one, and let's see if a is 0. Of course, if b is 0, then we've already got the result. We don't need to worry about it. Without this statement, the proof would take 3 times as long, because we'd have to show if a is not 0, then b is 0. If b is not 0, then a is 0. And it's also possible that a is 0 and b is 0. So we have to do 3 different things, and we don't want to do that. And since b is non-zero, that means that it has a multiplicative inverse, b inverse, where b times b inverse is equal to 1. So if I take the equation ab equals 0, and I multiply on both sides by that b inverse, on the left-hand side, I have b times b inverse, which is 1. On the right-hand side, I just proved that 0 times anything is 0. And one last step, anything times 1 is that thing. So I get that a is 0. And that's really all we need. Again, because we have that symmetry, right? A times b or b times a. It doesn't matter which one we call a and which one we call b. If we assume that one of these things is non-zero, then we have just proven that the other one must be 0. The zero product rule says if you have two things multiplied together, the result is 0. At least one of those things is 0. All right. So I would like you to play around with the properties of real numbers And again, just using those 10 properties, and you could use these two results that we just came up with, but you shouldn't need them. I would like you to try let's take any field R and let's take any element of that field that we'll call A. And our claim is that the opposite of A, the additive inverse, is the same thing as -1 times A. Once again, this is a property that you are very familiar with from your work in previous algebra courses. It's something that you use all the time. But it's not one of the things we listed as a property of a field, so we want to make sure that it actually does hold. So using the properties of the field that we listed, go through similar kind of derivation as we saw in the previous ones, and see if you can prove that the opposite of A is -1 times A. Right? Take some time to write that out, and I'll see you in the next video.